January 4th, 1945. Yokosuka Naval Air Technical Arsenal, Japan. Commander Takeshi Nakamura's hands moved slowly across the Grumman F-6F Hellcat's fuselage, his fingertips registering something his mind refused to accept. The aluminum skin felt impossibly thick, not the delicate 0.7mm sheeting that covered Japanese fighters, engineered to minimize weight at any cost. This was substantial, heavy, almost crude in its robustness. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. He rapped his knuckles against the cowling. The sound echoed solid and deep, nothing like the resonant ping of a Zero's lightweight construction. This American fighter that had force-landed near Kobe Airfield on Formosa 3 weeks earlier sat in Yokosuka's examination hangar, bearing the tail code 29 and bureau number 71441. Its pilot, Commander Robert August, was now a prisoner of war, but the aircraft itself was about to become something far more valuable to Japan than any intelligence extracted from interrogation. It was about to become evidence of a design philosophy so fundamentally opposed to Japanese aviation doctrine that examining it would force every assumption into question. Nakamura had spent 18 years designing fighters for the Imperial Japanese Navy. He had contributed to the Zero's development, that magnificent aircraft whose unprecedented range and maneuverability had shocked American forces at Pearl Harbor. He understood the mathematics of air combat with the precision of a man who had calculated wing-loading ratios and power-to-weight curves for every major Japanese fighter since 1936. And now, staring at this captured American fighter, every calculation seemed suddenly inadequate to explain what he was seeing. The Hellcat weighed 6,155 kilograms, empty. Intelligence reports confirmed this figure from multiple sources. The Zero weighed 1,680 kilograms empty, nearly 2,700 kilograms less, almost 4,000 pounds of weight difference between fighters designed for the same mission. Defending carriers, engaging enemy aircraft, achieving air superiority over contested airspace. Every principle Nakamura had learned at the Naval Academy, every lesson absorbed during his years at Mitsubishi's design bureau, insisted that lighter was better. Weight was the enemy of performance. Every unnecessary kilogram reduced speed, climb rate, maneuverability. The Zero had achieved its legendary capabilities precisely by eliminating everything non-essential. No armor plating, no self-sealing fuel tanks, no unnecessary structure, just enough airframe to hold the engine, weapons, and pilot. The minimum mass required for maximum performance, yet this American fighter, carrying nearly 2 tons of additional weight, had dominated Pacific skies for 18 months. Zero pilots reported the Hellcat was faster above 10,000 feet, climbed as quickly at altitude, and most devastatingly, survived battle damage that would have destroyed any Japanese fighter. The contradiction demanded explanation. How do you make an aircraft better by making it heavier? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Nakamura gestured to Lieutenant Yoshio Takahashi, his lead structures engineer. We will conduct a complete teardown analysis. Every system, every component. I want weight calculations for each element, material analysis, construction methodology, everything. Takahashi nodded, already pulling out his measurement tools and notebooks. The examination team assembled around the Hellcat consisted of 12 specialists, 3 structural engineers, 2 propulsion experts, 2 armament technicians, 1 electrical systems analyst, 1 hydraulics specialist, and 3 documentation clerks whose sole responsibility was recording every observation with photographic precision. They would spend the next 6 weeks systematically dismantling this aircraft, weighing components, analyzing construction methods, testing materials, but the first discovery took only 30 minutes and would fundamentally alter every assumption about aircraft survivability. The cockpit armor was obvious once you knew to look for it. Behind the pilot's seat, a steel plate approximately 8 mm thick formed a protective barrier between the seat back and the aircraft's rear fuselage. The plate covered the pilot's torso from neck to lower back, positioned to stop bullets and shell fragments approaching from the rear quarter, the most common attack angle in aerial combat. Nakamura ran his hand across the armored steel, feeling its weight, its solidity. He motioned for Takahashi to help him remove the pilot's seat to examine the protection more thoroughly. They disconnected mounting bolts and lifted the seat assembly free, revealing the full extent of American armored protection. The main backplate measured approximately 45 centimeters tall by 35 centimeters wide, 8 millimeters of hardened steel. Additional armor sections protected the pilot's head, with armored glass installed in the windscreen. Takahashi set the backplate on the hangar floor and produced his scales, 18 kilograms for the main plate. Additional armor sections total approximately 13 kilograms. Armored glass adds another 12 kilograms. Total pilot protection weight, 43 kilograms. 95 pounds of armor dedicated solely to keeping the pilot alive. Nakamura thought of the Zero's pilot seat, a thin aluminum frame with fabric covering. Total weight, perhaps 6 kilograms. The American fighter carried 7 times that weight in pilot protection alone. Test the steel, Nakamura ordered. Takahashi retrieved a 7.7mm rifle cartridge from the ammunition stores and secured the armor plate in a test fixture. At 10 meters range, he fired. The bullet struck the plate and ricocheted with a sharp metallic ping, leaving only a shallow crater on the surface. The bullet had not penetrated. He fired again. Same result. A third shot. The plate held. 7.7mm rounds, the standard ammunition for Japanese aircraft machine guns, could not penetrate this armor at point-blank range. Takahashi moved to 13mm ammunition, the heavier machine gun rounds used in some Japanese fighters. At 10 meters, the 13mm rounds made deeper craters, but still failed to penetrate completely. Only at 5 meters range did the 13mm rounds punch through, and even then, the plate absorbed enough energy that any bullet penetrating would be significantly slowed, its lethality reduced. Nakamura watched the test with growing comprehension of what this meant tactically. A Zero pilot attacking a Hellcat from behind, the standard approach for aerial combat, would fire 7.7mm rounds from perhaps 100 meters range. The bullets would strike the Hellcat's armored cockpit and fail to injure the pilot. The American would continue flying, maneuvering, returning fire. The Zero pilot would close range, firing continuously, burning through ammunition without achieving the critical pilot kill that ended combat. Meanwhile, the Hellcat pilot, protected by armor that Japanese Doctrine had deemed too heavy to justify, would maintain control, identify his attacker's position, and execute counter-tactics. The weight penalty that Japanese engineers calculated as unacceptable had translated into a decisive tactical advantage that rendered Japanese weapons partially ineffective. But the armor was only the beginning. The fuel system examination revealed something that would haunt Nakamura for the remainder of the war. The Hellcat's fuel tanks were not simple aluminum containers. Each tank was a complex assembly. An outer aluminum shell providing structural support, then layers of rubber compounds serving as self-sealing material, then an inner rubber bladder actually containing the fuel. When Takahashi cut into a sample tank section with his knife, the layered construction became visible. Outer shell, 1mm aluminum. First rubber layer, vulcanized compound, approximately 2mm thick. Middle layer, untreated natural rubber, 4mm thick. Inner bladder, fuel-resistant compound, 2mm thick. Total wall thickness, 9mm. Nakamura compared this to a Zero fuel tank, a simple aluminum container with walls approximately 1mm thick. No rubber, no layering, no protection. Just thin metal separating aviation fuel from enemy bullets. Takahashi had prepared a demonstration. He filled a section of Zero fuel tank with water and fired a 7.7mm round through it from 10 meters. The bullet punched clean holes through both sides. Water poured from both openings, streaming across the hangar floor, Flow rate, approximately 3 liters per minute from 2 holes, totaling perhaps 10 millimeters diameter. He repeated the demonstration with a section of Hellcat self-sealing tank. The bullet entered, and fluid began seeping from the puncture. But within 15 seconds, the flow slowed. After 30 seconds, it had reduced to a drip. After 1 minute, it stopped completely. The untreated rubber layer had absorbed fuel, swelled, and sealed the puncture. Takahashi examined the sealed hole with a magnifying glass. The rubber has expanded to perhaps 3 times its original thickness at the puncture site. The swelling creates a plug that blocks fluid flow. Even under pressure, the seal holds. The implications cascaded through Nakamura's understanding of aerial combat. A Zero, with bullet holes in its fuel tanks, would leak fuel continuously. The pilot faced 2 catastrophes: fuel starvation that would force him to abandon the aircraft within minutes, or fuel vapor, mixing with air to create explosive atmosphere, waiting for an incendiary round or spark to ignite it. Most Zero pilots shot down over the Pacific didn't survive because their aircraft caught fire. The fuel system, completely unprotected, turned each fighter into a flying bomb requiring only a single tracer round to detonate. American pilots had nicknamed the Zero the Flying Zippo for its tendency to explode in flames. Intelligence reports confirmed that Allied fighter pilots specifically targeted Zero fuel tanks because penetration guaranteed catastrophic results. The self-sealing tanks in the Hellcat changed this equation completely. A Hellcat struck by gunfire in the fuel system would seal the leaks, prevent explosive atmosphere buildup, and allow the pilot to continue fighting or withdraw to base. The aircraft might return with dozens of bullet holes in the tanks, but it would return. Takahashi weighed the complete fuel system components from both aircraft. Zero main fuel tank, 12 kilograms. Hellcat equivalent tank with self-sealing, 41 kilograms. Weight penalty for self-sealing protection, 29 kilograms per tank. The Hellcat has 6 tanks total. Total self-sealing system weight penalty, approximately 174 kilograms. 380 pounds of rubber and fabric, whose sole purpose was keeping damaged fuel tanks from killing pilots. This weight, added to the armor weight, accounted for more than 220 kilograms of the Hellcat's mass, nearly 500 pounds dedicated entirely to survivability rather than performance. Japanese Doctrine would have rejected this penalty instantly as unacceptable degradation of climb rate and maneuverability. Yet the Hellcat still outperformed the Zero in most combat scenarios. Nakamura pulled out his notebook and began calculations that would occupy his thoughts for weeks afterward. The math was straightforward, but the conclusion was devastating. Consider 2 fighters engaging in combat. Fighter A, the Zero, empty weight, 1680 kilograms. No armor, no self-sealing tanks. Pilot survives only if he avoids all enemy fire. First hit to fuel system creates fire hazard. Second hit likely causes catastrophic fire. Pilot survival rate when hit, approximately 10%. Fighter B, the Hellcat, empty weight, 6155 kilograms. 220 kilograms of armor and self-sealing protection. Pilot survives multiple hits to protected areas. Fuel system damage seals automatically. Pilot survival rate when hit, approximately 70%. Now extend this through a combat tour. A Zero pilot flying 30 missions, each with 10% chance of being hit by enemy fire, has cumulative survival probability of approximately 26%. 74% of Zero pilots will be killed or badly wounded before completing a standard tour. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. A Hellcat pilot flying 30 missions with same hit probability but 70% survival rate. When hit has cumulative survival probability of approximately 79%. More than 3/4 of Hellcat pilots survive their tours. The weight penalty that seemed unacceptable in initial design calculations translated into survival rates 3 times higher than unprotected Japanese fighters. and survival meant experience. A pilot who completed one combat tour gained knowledge that made him more effective in subsequent missions. He learned enemy tactics, developed situational awareness, mastered his aircraft's capabilities. An experienced pilot was worth 5 inexperienced pilots in combat effectiveness. American pilots survived to gain experience. Japanese pilots died before accumulating it. The mathematics of attrition warfare, Nakamura realized with cold certainty, favored the side that brought pilots home. The side that sacrificed some performance to ensure crew survival could sustain combat operations indefinitely because experienced pilots kept flying, kept training new pilots, kept transferring knowledge. The side that optimized purely for performance, accepting pilot casualties as the price of aircraft capability, would eventually run out of pilots no matter how magnificent their aircraft were. Japan was running out of pilots. The engine examination revealed further evidence of American design philosophy that prioritized reliability over theoretical performance. The Pratt & Whitney R2-800 double wasp that powered the Hellcat was a monster of an engine. 18 cylinders arranged in 2 rows, displacing 2 800 cubic inches, producing 2,000 horsepower at takeoff settings. Nakamura's propulsion specialists spent 3 days disassembling the engine, measuring components, analyzing construction methods. What they found contradicted everything about Japanese engine design philosophy. Chief Engine Analyst Kenji Yamamoto presented his findings on the 4th day of examination. The cylinder construction uses relatively simple cooling fin designs. Straight fins, uniform spacing, nothing complex. This allows mass production on automated machinery. He showed Nakamura a cylinder head from the R2-800 alongside a cylinder from a Nakajima Saki engine used in the Zero. The Japanese cylinder featured intricate curved cooling fins, individually machined to optimize airflow and heat dissipation. Beautiful engineering. The American cylinder looked almost crude by comparison, its fins simple and regular. The Japanese cylinder provides approximately 8% better cooling efficiency, Yamamoto continued, but it requires 14 hours of skilled machining to produce. The American cylinder requires 3 hours of semi-automated manufacturing. He paused, letting the implications settle. The American cylinder is 92% as good, but American factories can produce 5 of them in the time we produce 1. Nakamura examined the American connecting rods, the critical components translating piston motion into crankshaft rotation. The rods were forged from standardized steel alloys, heat-treated for strength, finished with basic machining. Japanese connecting rods used exotic metals selected for optimal strength-to-weight ratio, individually balanced to reduce vibration, polished to eliminate stress concentrations. American connecting rods are 12% heavier than our equivalent components, Yamamoto noted. But they are manufactured from steel alloys available in bulk quantities. Our rods require specialized metals that are increasingly difficult to obtain as the war continues. The pattern repeated through every engine system. American designers had chosen readily available materials, simple manufacturing processes, and robust construction that sacrificed marginal performance gains for massive production advantages. The R2-800 engine was not optimized for maximum theoretical horsepower per kilogram. It was optimized for reliable production of adequate horsepower, using materials and processes that could scale to industrial quantities. Yamamoto's most significant finding concerned engine reliability. We examined wear patterns on internal components. This engine shows consistent operation for approximately 400 hours between major overhauls. Cylinder walls display even scoring. Bearing surfaces show minimal degradation. Piston rings maintain adequate tension. He presented comparative data from Nakajima Saki engines captured from downed Zeros. Our engines show severe wear patterns after approximately 150 hours. Cylinder cooling fins crack from thermal stress. Connecting rod bearings require replacement. Complete overhaul necessary. The maintenance implications were staggering. An American carrier could keep its fighters operational for months at sea, performing routine maintenance but avoiding major overhauls. Japanese carriers needed to return to port every few weeks for engine work that required specialized tools and trained mechanics. American pilots could trust their engines to perform reliably mission after mission. Japanese pilots flew aircraft whose engines were consuming themselves through operation, each flight hour bringing them closer to catastrophic failure. Nakamura thought of the resource implications. Japan was training replacement pilots as quickly as possible, but the training pipeline took months to produce combat-ready aviators. Meanwhile, experienced pilots were dying in aircraft that caught fire from single hits, flying engines that failed after 150 hours, attacking enemies protected by armor that Japanese weapons couldn't penetrate. The Americans were building fighters that brought pilots home. Japan was building fighters that killed the pilots flying them, if not through enemy action, then through inevitable mechanical failure or vulnerability to damage. After 2 weeks of intensive examination, Nakamura compiled his preliminary findings into a 23-page technical report. The document detailed every measurement, every test, every comparison between American and Japanese design philosophy. But the conclusion could be summarized in a single devastating paragraph. The F-6F Hellcat represents a design philosophy fundamentally opposed to Imperial Japanese Navy doctrine. American engineers have prioritized pilot survival, operational reliability, and ease of manufacture over maximum theoretical performance. The resulting aircraft is heavier, uses more resources per unit, and achieves lower peak performance specifications than equivalent Japanese fighters. However, these apparent disadvantages translate into decisive tactical superiority through higher pilot survival rates, better operational availability, and sustainable production rates that Japan cannot match with current industrial capacity. The weight penalties that Japanese doctrine considers unacceptable are precisely the features that make American aircraft superior in sustained combat operations. Nakamura submitted his report through proper channels on January 19, 1945. He received no acknowledgement, no questions, no requests for clarification. The document disappeared into the Navy Ministry's filing system, where uncomfortable truths went to be officially ignored. But Nakamura knew he was not alone in seeing what he had seen. Evidence was accumulating from multiple sources. The B-17 Flying Fortress that arrived at Tachikawa Army Air Technical Research Institute in May of 1943 represented an even more profound challenge to Japanese understanding of aircraft design than the captured fighters at Yokosuka. Major Kazuyuki Saito watched as technicians carefully positioned the massive bomber in the main examination hangar, its 4 Wright Cyclone engines silent after the long journey from Java, where Japanese mechanics had rebuilt it from salvaged components. The B-17E stretched over 20 meters from nose to tail, its wingspan exceeding 31 meters. Empty weight, 16,390 kilograms, more than 9 times heavier than a Zero fighter. Yet this 4-engine bomber had crossed thousands of kilometers of Pacific Ocean, survived combat damage that should have destroyed it, and delivered tons of explosives onto Japanese targets before mechanical failure finally forced it down in territory Japan controlled. Saito had been briefed on the strategic threat B-17 seconds represented. American bombers operating from bases in China and later from captured Pacific islands could strike Japanese industrial facilities, supply, depots, naval bases. Each raid destroyed production capacity Japan could not easily replace. Understanding how Americans built bombers that could absorb such punishment while maintaining operational capability was now a strategic priority equal to any tactical concern. Designer Kikuhara Shizuo, who had originated the Kawanishi H-8K Emily flying boat, joined Saito's examination team specifically to analyze the B-17 system's integration. Kikuhara's first observation, after walking around the bomber, captured what would become the team's central finding. The Americans have perfected subsystems to such a degree that a minimum of controls are needed in the cockpit. Everything is standardized, simplified, designed for operation by adequately trained crews rather than specialists. The B-17's construction methodology was immediately apparent. The entire aircraft was assembled using welding rather than riveting. Japanese doctrine still considered riveted construction superior for aircraft structures, believing welded joints created stress concentrations that would fail under combat loads. Yet this B-17 had crossed an ocean multiple times, absorbed flak damage, and remained structurally sound. Saito ordered stress testing on welded joints removed from the airframe. His structures team applied loads equivalent to 6 times normal flight stress. The welds held. They increased load to 8 times normal stress. The welds still held. Only at loads exceeding 12 times normal flight stress did the welds begin to fail, and even then, the failure was gradual rather than catastrophic, the metal deforming plastically before finally separating. Welded construction is actually superior under combat damage scenarios, Saito's lead structures engineer reported. Riveted joints concentrate stress at rivet holes. Battle damage to riveted structures can propagate rapidly as rivets pop out in sequence. Welded structures distribute stress more evenly. Damage remains localized. The aircraft maintains structural integrity even with significant damage to individual sections. The construction method also had profound manufacturing implications. Welding required less skilled labor than precision riveting. Welders could be trained in weeks rather than the months needed to develop skilled riveters. Welded structures could be assembled faster, with fewer workers, using less complex tooling. Japanese aircraft manufacturers employed master craftsmen who spent years learning to install rivets with perfect precision. American manufacturers employed semi-skilled workers who learned to run welding equipment in basic training programs. One approach created works of art. The other created works in quantity. The fuel system examination revealed protection measures even more extensive than those found in the Hellcat fighter. The B-17 carried 8 fuel tanks distributed throughout the wings and fuselage, total capacity approximately 9,200 litres. Every tank featured self-sealing construction, but the bomber's tanks used thicker rubber layers than fighter tanks, providing protection against heavier weapons that bombers faced from ground-based anti-aircraft guns. Saito's team test-fired various weapons at B-17 tank sections, 7.7mm rounds sealed within seconds, 13mm rounds sealed within 30 seconds, even 20mm cannon shells, which blew massive holes through the tank walls, were partially sealed by the rubber compounds, reducing fuel loss enough that the bomber could potentially reach base before tanks ran dry. The weight penalty for this level of protection is approximately 300 kilograms per aircraft, Saito calculated, but the survivability advantage means bombers can complete missions despite damage that would force Japanese bombers to abort or crash. The armor protection throughout the B-17 was comprehensive in ways that shocked the Japanese examination team. The cockpit featured armored glass windscreens, steel plates protecting pilots from frontal attacks, additional plates shielding the bombardier position. The waist gunner positions included protective shields. Armored bulkheads compartmentalized the fuselage, preventing battle damage in one section from spreading throughout the aircraft. Total armor weight, approximately 800 kilograms, nearly a ton of steel whose sole purpose was keeping crew members alive. Saito thought of Japanese bombers like the G-4M Betty, which carried no armor protection at all. Betty bombers had earned the nickname Flying Lighter from their crews because they ignited so easily when hit. American pilots called them one-shot lighters for the same reason. Now, Saito understood why. The defensive armament installation revealed yet another manifestation of American design philosophy. The B-17 carried 1350 caliber machine guns, positioned to provide coverage against attacks from any angle. But what impressed Saito was not the quantity of weapons, it was their installation methodology. Every gun mount used standardized brackets. Ammunition feed systems were identical across all positions. Gun barrels could be changed in minutes, using simple tools. Spent shell collection systems prevented brass casings from interfering with aircraft controls. The entire defensive system was designed for rapid maintenance and repair by crew members with basic mechanical training. Japanese bomber defensive systems, by contrast, used custom installations for each gun position. Maintenance required specialized knowledge of each unique mounting system. Battle damage to one gun position often affected nearby systems because of complex mechanical interconnections. American designers had created modularity. Japanese designers had created integration. One was easier to build and maintain. The other was more elegant engineering. In peacetime, elegance might matter. In war, Saito was learning. Only effectiveness mattered. The fire control system that coordinated the B-17's defensive guns represented technology Japan had attempted but never successfully implemented. A central computing site allowed the top turret gunner to calculate lead angles for moving targets, automatically adjusting for aircraft speed, target speed, and ballistic drop. The system wasn't perfect, but it improved hit probability enough to make attacking B-17 formations significantly more dangerous than attacking uncoordinated bombers. By Japanese standards, the B-17's fire control system was very advanced. Saito's team spent days analyzing its operation, photographing components, creating drawings. The technology would later influence development of Japanese fire control systems, though Japan would never achieve the integration and reliability the Americans had demonstrated. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The most revealing discovery came from examining the B-17's production documentation, which had been recovered intact from the crash site. A builder's plate mounted in the engine control room provided construction data. Kaiser shipyards had built ships, but Boeing built this bomber. The plate read, Boeing Aircraft Company, Seattle, Washington. Airframe serial number 41 to 2471. Manufactured November 1941. But it was the maintenance log that told the real story. The aircraft had flown 437 combat hours before mechanical failure forced it down. 437 hours of operations, including dozens of missions over enemy territory, exposure to extreme weather, combat damage, and repair, all supported by standardized maintenance procedures that any trained mechanic could perform. Saito compared this to Japanese bomber operational experience. The G4M Betty required major engine overhauls every 150 hours. Airframe stress, inspections every 200 hours, complete systems overhaul every 300 hours. Each overhaul required specialists and consumed resources Japan increasingly lacked. The Americans had built bombers that kept flying. Japan had built bombers that required constant attention to remain operational. In the crew quarters, Saito found something that crystallized the entire philosophical difference between American and Japanese aviation. Posted on a bulletin board was a checklist for pre-flight inspection. External visual inspection, 15 minutes. Engine systems check, 10 minutes. Flight control verification, 5 minutes. Fuel and hydraulics, 10 minutes. Radio and electrical, 5 minutes. Total pre-flight time, 45 minutes. Japanese bomber pre-flight inspections required 3 hours minimum, often longer. The difference wasn't that American crews were less thorough. The difference was that American aircraft were designed to be inspectable quickly. Systems were accessible. Problems were obvious. Checks were standardized. Japanese aircraft required lengthy inspections because systems were complex, access was difficult, and problems required specialist knowledge to identify. One approach maximized sortie rate. The other maximized engineering elegance. In sustained operations, sortie rate determined effectiveness. Saito's complete technical evaluation ran to 41 pages with extensive photographic documentation. He submitted it through Army Air Force channels in August of 1943. Like Nakamura's Hellcat report, it disappeared into the bureaucratic system without acknowledgement or response. The institution had received the information. The institution chose not to act on it. But knowledge, once gained, could not be completely suppressed. Engineers at both Yokosuka and Tachikawa now understood what made American aircraft effective. Some attempted to apply these lessons to Japanese designs. In September of 1943, Nakamura proposed modifications to the A6M50 variant that would incorporate limited protection measures without completely compromising performance. His proposal specified 8mm armor plate behind pilot's seat, weight penalty 32 kilograms, 55mm armored glass windscreen, weight penalty 8 kilograms, limited self-sealing protection for main fuel tank only, weight penalty 43 kilograms, total additional weight 83 kilograms. The modification would reduce zero top speed by approximately 17 kilometers per hour. Climb rate would decrease by roughly 9%. Range would drop by approximately 350 kilometers, but pilot survival probability would increase by an estimated 40%. Navy procurement reviewed Nakamura's proposal for 6 weeks before rejecting it. The official response stated, "The proposed modifications would degrade the A6M5's performance below acceptable standards. The Zero's superiority depends on maximum maneuverability and speed. Adding weight contradicts fundamental design philosophy. Proposal rejected." The rejection included no analysis of whether pilot survival might be worth modest performance reduction. No calculation of how experienced pilots surviving combat tours might improve overall squadron effectiveness. No consideration of whether Japan could sustain current loss rates indefinitely. The institutional response was pure doctrine. Performance above all else. Weight was the enemy. The Zero must remain the lightest, most maneuverable fighter in service. That this made it the most vulnerable fighter in service was apparently irrelevant. Other designers met similar resistance. Proposals to add self-sealing tanks to the G4M Betty bomber were rejected as too heavy. Suggestions to armor the cockpit of the Ki 43 Oscar fighter were denied as compromising agility. Recommendations to simplify manufacturing processes for easier mass production were dismissed as inferior. Craftsmanship. The institution had access to complete technical intelligence about why American aircraft were succeeding. The institution chose to maintain existing doctrine despite evidence that doctrine was failing. Some modifications did eventually reach production aircraft, but too late and too limited to matter strategically. Late War Zero variants received 8mm armor plates and 55mm armored glass. But these partial measures arrived in 1944, when Japan had already lost air superiority. The modifications slowed already marginal fighters without providing the comprehensive protection that might have improved survival rates significantly. The self-sealing tank situation proved even more problematic. When Nakajima attempted to install self-sealing fuel tanks in the B-6N Tenzan torpedo bomber prototype, fuel capacity decreased by 30%. The range reduction was unacceptable for a carrier torpedo bomber that needed to strike enemy fleets at maximum range. Production aircraft reverted to unprotected tanks. Crews would fly combat missions knowing that a single bullet in their fuel system meant probable death. This was not because Japanese engineers couldn't build self-sealing tanks. Captured examples had been thoroughly analyzed. The technology was understood, but implementing it meant accepting range penalties that Japanese doctrine wouldn't permit. American forces had accepted those penalties. The North American B-25A bomber lost 218 liters of fuel capacity when self-sealing tanks were installed. A 23% decrease. The P-38D fighter dropped from 410 gallons to 300 gallons when self-sealing tanks were added, a 27% reduction. American designers accepted these losses and compensated later. The P-38J added wing leading-edge tanks when intercoolers were repositioned, restoring original capacity. The B-25 received optional bomb bay fuel tanks for ferry flights. American doctrine treated range reduction as a problem to be solved through engineering iteration. Japanese doctrine treated range reduction as fundamental violation of requirements. If self-sealing tanks reduced range, then self-sealing tanks were unacceptable. There would be no engineering iteration, no creative solutions, no willingness to compromise sacred performance specifications. The industrial capacity gap made the problem worse. Even if Japanese doctrine had permitted adding protection systems, Japan lacked the manufacturing base to implement them across the entire aircraft fleet. Self-sealing fuel tanks required rubber compounds in quantities Japan could barely supply. Armored steel required metallurgical capacity, increasingly strained by ship and tank production. Manufacturing standardization required retooling factories that were already struggling to maintain current production rates. By late 1944, the material situation had become desperate. Aluminum alloy allocation was insufficient to meet aircraft production quotas. Engine manufacturers competed for high-grade steel that existed in inadequate quantities. Rubber was so scarce that tire production for aircraft landing gear was being rationed. Adding hundreds of kilograms of protection materials to every fighter and bomber was economically impossible, regardless of whether doctrine permitted it. The captured aircraft examinations had revealed what Japan needed to do. Industrial reality made doing it impossible. Nakamura watched American air superiority become absolute through 1944 and into 1945. F-6F Hellcats ranged freely over Japanese-controlled territory, their pilots gaining experience through combat survival, their aircraft absorbing damage that would have downed unprotected Japanese fighters. B-17 seconds, and later B-29. Superfortresses struck Japanese industrial facilities with systematic precision, their crews protected by comprehensive armor, their fuel systems surviving flak damage that would have destroyed Japanese bombers. The Great Marianas Turkey shoot in June of 1944 saw devastating Japanese losses, over 500 Japanese aircraft destroyed in a single engagement. American losses, approximately 43 aircraft in combat, with 80 more lost to operational accidents during night carrier landings and fuel exhaustion. But operational accidents could be addressed through better procedures. Combat losses were the measure of aircraft effectiveness. Japanese pilots flew aircraft optimized for performance, but unprotected against damage. American pilots flew aircraft optimized for survivability with adequate performance. In sustained combat, survivability determined which pilots lived to fight again. Experience accumulated among survivors. Inexperience accumulated among replacement pilots trying to fill positions vacated by the dead. By early 1945, the qualitative gap had become as significant as the quantitative gap. Veteran American pilots with hundreds of combat hours faced inexperienced Japanese pilots with perhaps 50 hours of flight training total. Aircraft quality mattered less than pilot quality, and pilot quality depended on survival. The final captured aircraft examination Nakamura conducted came in March of 1945. An F-4U Corsair had force-landed near Kasumigora Flight School after sustaining battle damage. Japanese mechanics had repaired it using fabric patches over damaged wing sections and spare parts salvaged from other crashed Corsairs. The repaired aircraft bore the scars of combat. Bullet holes sealed with aluminum patches, replaced panels mismatched in color, control surfaces that had been straightened after impact damage. What shocked Nakamura was that the aircraft was still flyable after repairs performed by mechanics with basic tools and limited spare parts. The Corsair had been designed for field maintenance. Damaged sections could be patched with materials available at forward bases. Critical systems were accessible without extensive disassembly. Redundancy meant that multiple failures were required to ground the aircraft completely. Japanese fighters, by contrast, required specialized facilities for most repairs. Battle damage often meant the aircraft was written off entirely because repair was more resource-intensive than building new fighters. American aircraft were designed to be repaired. Japanese aircraft were designed to be perfect initially, with the assumption that perfection would prevent damage. Nakamura noted with professional admiration that the Corsair wing, despite being constructed partially of fabric, was stronger than the all-metal Zero wing. "We were surprised there were places on the wing covered with fabric," he wrote in his examination report. Yet these fabric sections, when tested, showed superior strength to weight characteristics compared to our all-metal construction. The Americans use materials appropriately rather than assuming metal is always superior. It was a small observation but representative of the larger pattern. Japanese designers had assumed all-metal construction was modern and superior. American designers had used fabric where fabric performed adequately, reserving metal for locations where it was necessary. One approach prioritized engineering purity. The other prioritized practical effectiveness. Nakamura's final report, submitted in April of 1945, summarized findings from examinations of 6 different American aircraft types. The F-6, F Hellcat, F-4U, Corsair, P-51 Mustang, B-17 Flying Fortress, B-24 Liberator, and P-38 Lightning. Every aircraft exhibited the same design philosophy: pilot protection prioritized over maximum performance, reliability emphasized over theoretical efficiency, ease of manufacture and maintenance valued more than engineering elegance. Up next, you've got 2 more and standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.